have been going solar crazy around here. We've got a full Tesla slab up against the wall that I'm going to show you next episode, and all of it working, charging off solar and through an inverter, running our whole shop. But I think most people immediately, it's going to take a while to work up to the full Tesla battery pack. We still have some development work to do on the software. A little bit here, but we've come quite a ways. If you recall, we had a little 20 kilowatt thing on the bench there with a green box and a spaghetti. But increasingly, solar installations are becoming more professional. And after conferring with our friend Joe Sidebottom in Florida, this is what he likes, is a 36 by 30 by 12 inch Wiegman NEMA 12 package enclosure made out of 12 gauge steel, powder coated, and very professional. So we have built our controller and our system into this box with 6 Tesla battery modules for a total capacity of it'd be 43.2 volts nominal, 48 fully charged, but 43.2 volts at 705 amp hours total for the 6 modules, or 30,486 watt hours of storage capacity in one box. Now the modules are 56 pounds a piece, so that's about 336 pounds of modules. I would call this about 375 pounds for the package. And we've been putting it together. I've got some clips, step by step, of what we've done, and I think you're going to want to see that. And we'll talk more about why in a little bit. Let's take a look at what we've done to put this together so far. Okay, we're here with Dylan Freeze and a 48 volt, 30 kilowatt battery, but we're right now working on the NEMA container for it. Dylan, what have you got done?
Well, as you can see out here on this side, we've got some holes drilled in the bottom of this NEMA box. Here's a Rebling connector. These are used on like aircraft. They're, pretty heavy duty. They'll do up to 700 volts and 1,300 amps, I believe. But yeah, these things are pretty.
And that's where your 48 volts comes out, right?
Right. Yeah. And then so over here we've got our CAN 1 port. This is for right now. Currently, this is for our inverter, and the only inverter right now that we're supporting is the Sunny Island. But so this is the port for that, and then also we've got our CAN 0 port, and that would be for kind of like for monitoring the batteries internally. And
those are some Amphenol 2-pin bulkhead connectors, IP57, weatherproof, and all that.
Yeah, they're great. These connectors are great to work with. A lot better than our jacks from our previous build. But
we've given up on the audio jacks.
Yeah, and then up here we've got our IP57, our USB port for tying into the. That's hooked in, and I'll open this so you can see. It's what these screws are for to our Arduino DUI and our shield. But
and this lower one, charge enable, that's 12 volts and switch ground.
Yes, right. Yep. To charge a MPPT or something like a charger, external contactor or something like that.
Right, an external contactor to turn on an EV charger or a solar MPPT charge controller. What's on your panel here?
Up here we've got we got 2 LED lights and a switch. Once I switch this we'll get 12 volts from we've got a DC, and I'll show you a converter down there. It'll convert the 48 volts to 12 volts DC, at which point our contactor will close, and then our negative contactor will close for our pre-charged circuit, and then the second contactor will close, and we'll have a live battery at that
red
point.
is the negative contactor, green is the positive contactor.
Yeah.
And we've got a configurable pre-charge where it pre-charges across the resistor across the positive contactor. Okay. And that switch energizes your whole 12 volt bus in there, powering everything up from a DC to DC converter.
Yep.
Okay. All right, Dylan, let's show me what we got inside here. Start with your switches and LEDs.
Yeah, so we were just talking about how we've got a harness that kind of runs down here. This is, we've got them all wrapped around each other so we don't have this just rat's nest out here. I think it looks pretty clean, but it'll come down, and then once we hit that switch, so we've got our 48 volts coming into this DC-DC converter, at which point it runs up and snakes all the way to the switch, back down to this bus bar here. And once we hit that switch, it'll apply power to all of these.
So you have 12 volts on one side of the bar and ground on the other.
That's right. Yep. So yeah, we've got ground over here and power over here, as you can see. And once we do that, that applies power to everything. The contactors, well, first our board and the shield, and we've got it programmed to, for our pre-charged circuit to close the negative contactor first. Here's our pre-charged resistor there, and
that's across the positive contactor.
That's right. Yeah.
So we close the negative contactor, and we can charge the external circuit through that 25 ohm 50 watt resistor. And you've got two taps there on the input side of the contactors. That goes to that DC to DC converter. That's where it gets the 48 volts.
Right,
to
yep.
convert to 12. And you're actually connected to the Wiegman with copper bars. That looks like a pretty neat deal.
Yeah, yep. Those are 3/8, or I think, yeah, 3/4 inch copper bar.
And that's your limb cab 300 current sensor.
Yeah.
That'll go on the cable going to the negative contactor. And then you've got a cable coming off the shield. This is what goes to the individual battery modules.
Yep.
And we'll hook a harness into that, and then that'll connect to each of the BMS boards.
Yeah, and they kind of daisy chain each one of these modules together, and so that, I guess that would be the next step from here.
Yep, we'll put a couple of modules in. I see you've got some threaded rod in place.
Yep.
For that, and down here is our AN4 side. You have an AN4 to AN6 through bulkhead connector, and we'll use AN4 braided.
Yeah. Bill made this up for us. These are kind of cool. We've got a little segment on that if we pan to that, but it's they're pretty neat how they work, and Bill's kind of got a little video to explain how that's done. So.
And that's 350 psi braided. A little bit of a step up from the plastic tubing Tesla uses, and that's how we're going to connect all the coolant connections on the battery modules. Okay, so what's next? We put in a couple of modules and get started laying them up, huh?
I think so, and try not to blow anything up.
All right, well, let's keep after it.
All right,
some further work on the NEMA 36 by 30 inch by 12 inch thing. We put in two battery modules. You notice over here we've added a fuse and copper strap to that, and tied that negative terminal of our first two batteries to the negative contactor. One of the things we haven't mentioned yet is these contactors actually have a set of auxiliary contacts, and so we can run 12 volts from our block over here to those contacts, and we come off the other side of the contact, and that is what lights the LED. It also goes to our digital inputs, each one to a different digital input, to our Tesla battery module controller shield. And in this way, I can actually check and see if the contactor did close, and in fact, if it did open. And this is kind of important in the case of welded contactors. Here's one of our 70 millimeter battery straps that connects the two modules, and here we take off our positive. Now on each side you see these copper straps we have here that will go on to the next module level, and so we will have eventually 6 modules, and that'll be 2P or 2S 3P. In other words, 3 parallel strings of 2 series modules. Here is a little 2 connector version of our wiring harness, and that connects to this we showed you earlier. That connects us to our controller and lets us read 6 cell voltages per module, the module voltage, and the temperatures of both the positive and negative terminals of the module itself. Let's take a look at the other end. On this end, we have the bottom of the modules, and you can see here we have a 350 psi nylon braided hose connected to the connector of the first module with a 1/2 inch hose clamp, and then we connect the output of that module to the input of the next one, and we have the output of that one hanging free. It will connect to the next row above, but the trick here is the insertion of these 1/4 inch ultra high molecular weight polymer U-channels, and here's a piece of it, as you can see, kind of a U-channel, and those will actually also be used across the batteries to hold them down with the threaded rod, and we'll have a piece of aluminum bar that sits in there. That'll spread the pressure across the modules very nicely, and of course ultra high molecular weight polymer is it has a very high dielectric. It won't conduct at all. And so we did our hosing up, stuck in the UHMW blocks, and then slid the batteries down on the bottom, and those blocks will give the modules something to rest on. If you hang this on a wall or stand it up, the batteries won't be standing on the case wall. They'll be offset by these very strong UHMW polymer blocks, and we'll do that with each row of them and continue our connections with the nylon braided hose. It's a 4AN hose, and that's exactly the right size for the 1/4 inch inner diameter that we need to fit securely on the Tesla cooling fittings. Those fittings are connected to some sort of flat channels that weave in and out among all those individual cells, and so it's a very effective way of heating or cooling them. And I would expect that in most cases we're not going to need to do any heating or cooling under the kind of loads we typically see in a solar installation. But we're going to hose this up and have it available here, these fittings, and if you're in some sort of temperature extreme, or particularly if you're going to use these outside in the winter, one restriction on these lithium cells is you simply cannot charge them at all, not a little bit, but at all below freezing. And so that's what we've got going there. There's our fuse. It's our typical 300 amp slow blow fuse we use in the cars, and that will prevent, in the unlikely event of an external short, this will blow. It doesn't blow right at 300 amps. You can run 300, 400, 500 amps through here for some period of time, but as the current increases, the time gets shorter, and they call it a slow blow. And it's very capable of breaking high voltage connections, so this 48 volt application will be fairly trivial for it. And that's where we're at next, I guess, is to add another rank of battery cells and bring this up further. Okay, here we go. We've added another layer of battery modules, so we have 4 modules total now. Added our copper strap here for the next row. Replaced our 2 module harness with the 4 module harness for testing, and have it all hooked up. This end, of course, we connected the lower rank to this one, and then loop these 2, and we'll connect this one to the far end of the next level and bring that back, and then take it out here for the shortest distance to our thing. And of course, we've added more of the ultra high molecular weight blocks, another layer of those to act as standoffs at the bottom. And that's pretty much our second layer of cells. We'll add one more, and really that should bring us to 6 battery modules, and that will give us really about 33 kilowatt hours of capacity. We're calling it a 30 kilowatt hour battery, but that will really be the usable, treating them fairly gently. So you'll have a 30 kilowatt hour pack in a 36 by 30 by 12 inch enclosure, carbon steel enclosure, and hopefully for about $9,000. LG Chem has introduced a battery using similar cells, 9.8 kilowatt hour, 9.5 kilowatt hours usable. I think they've got a price for about $4,500, and this would serve as 3 of those, over 3 of those, and this will be in one box. So I think this could be a big boon. You can power a house for quite a while on 30 kilowatt hours of batteries. As I say, I installed 50 kilowatt hours of Trojan deep cycle cells in 1998. We never drew them down to even close to the bottom, even once. But I think they were $15,000 then for lead acid. So this will be comparable to lead acid prices for a lithium battery that should last for a dozen years. Stay with us. In our final stage, we put our top layer of battery cells in, completed our hosing for the coolant system, which we're going to provide, and secured it all on our threaded rods with some 1-inch just light aluminum tubing, but we cushioned that with some more of our ultra high molecular weight U-channel, and that presses down very gently on the batteries and holds them in position very strongly. We've put a fuse in on the negative terminal, and we've added our brand new wiring harnesses that we got from SGW out in Santa Barbara, and that's made for a very professional installation. We close the lid, push the button, it comes up. Right now I've got it charging with a brand new Schneider 80-600 charge controller. We had a few problems with the Morning Star, and it didn't put out much power. This will do about 4,800 watts at maximum, but it's limited to 80 amps into our 48 volt battery, and so it'll be a little less than that max power, and that's coming in. We have, as you saw in the build, put in our AN4 tubing and fittings and our bulkhead connectors, and we have that run over here. Can you show it a little bit, Dylan? Wake up. With our pump cart and our pumping fluid through here. I don't think in most normal operation, you're going to need heating and cooling, but we decided to set it up and see what we could do for 2 reasons. In some ambient conditions and putting out into high power situations, you could develop some heat. The other thing is that in colder climates, one of the big issues with these cells and with all lithium cells is you do not want to charge them below freezing. That's 0 degrees centigrade, 32 degrees Fahrenheit, and if you do, it will cause lithium plating on the anodes, and it's irreversible damage. And you could damage the cell sufficiently that then when you charge it fully, it goes incendiary. Again, that would show up in an imbalance as you charge the cells, and our software will catch that and disconnect you from the pack. We have our pack connected with our Ribbling connector. We're just using some 4-aught here, but it'll take 2-aught very well to our battery bus. We've got our CAN output. We have 2 CAN ports and 2 sort of auxiliary 12-volt ports output, and the CAN is to run the Sunny Island 6048, requires a BMS for lithium batteries, and requires CAN commands, and we have built that into the software. This is our charge control, charge enable. The Schneider, an interesting tale. I found a guy on eBay named John Mayton. John is been a solar installer for 30 years, he says, meaning he's been installing photovoltaics since 1985. I'm going to call bullshit on that from the beginning. And then I should have known from that what I was getting into. And he's got thousands of happy, enthusiastic customers, and knows everything about solar, and if you have any questions, he'll be very happy to answer them. And he was offering this Schneider. I said some of the Schneider equipment requires this SCP control panel, a Schneider control panel, to be able to do anything with it. Does this device require that SCP? And he came back and told me, oh no, it doesn't. It's got a menu on it. And I said, great. And I ordered it and bought it and got it in. I'm very pleased with it, actually. It puts out a great deal of power, but there's no way to configure the batteries. And there is no menu. I said, John, what is this? There's no menu that I can see. And he came back and says, oh, I am so sorry. I made a mistake. It does require the controller, and I'll be happy to sell you one. I said, pardon, you already told me I didn't need one. Now, if I do, I think you ought to send it to me. Well, no, I'm not going to do that, but, you know, I don't know why you're taking such a hard line on that, Jack. I mean, I've got 500 happy customers and have been doing this for 30 years. And the guy at the factory told me that it didn't, and then on later he told me it did. And it's really the guy at the factory's fault. I said, John, if you've been doing it for 30 years, I assumed you knew. That's why I asked you the question. And so I got this thing without the controller. Fortunately, would you believe, I don't think it matters. We can get the controller, and you can customize the battery charging. But in its native state, all the voltages it uses are so far beyond ours that it just charges in the bulk state all the time when charging our battery. And so we use our charge enable output to simply switch on and off the solar to the Schneider. And so it's always charging at full rate, but we can turn it on and off and enter a cutoff and enter a resume in the battery. The brain should be in the battery. The battery knows what it needs. Why they keep trying to put it all in these devices, I don't know. We have another output here that I can program for about anything. And again, these outputs are constant 12 volts. It always has 12 volts, but we switch the ground. And so that's the operator relay or whatever. Joe Sidebottom wants a TTL output for some device, and I'm working on a little circuit that'll convert that 12 volts and switch ground to an off and on, 4.5 volts or so that he can use for a transistor to transistor logic input. But this output right now I have set on as a heat enable, and it will turn on your pump and your fan for your environmentals that pump fluid through the battery. Now, why do I call it heat enable? Well, I think the most important thing is to heat it, but you can use it to switch either one depending on the season. It works on the already entered high temperature alarm and the low temperature alarm. And so when you get 3 degrees above the low temperature alarm, this output will go high. And it'll stay high until you're 10 degrees above the low temperature alarm. On the other end, with your high temperature alarm that you can set it to whatever temperature you want in centigrade. If it gets within 3 degrees below the high temperature, it will come on, and it will stay on until it falls back down to at least 10 degrees below your high temp alarm. So we use the high and low temp alarms to key the heat enable or cool enable output on this. Of course, we've got an LED for our negative contactor, LED for a positive contactor, and again, you have a variable pre-charge you can set. We do have, this is our 4th prototype of the Shield, and we're going to sell this as a controller. The main controller is really just an EV-TV DUI, but then we have the Shield with it that has a 20-pin value lock output, and we give you a little diagram of how that works with our system. Your mileage may vary. You have 4 switched digital outputs, as I said, and we tried several things, but we eventually went back to the somewhat expensive but very capable gate drivers and 6 amp MOSFETs that we use on the JevQ. I think Colin put a 2.5 amp PTC on there, and a very nice Schottky diode to protect from to suppress transients. We also have 4 digital inputs, and they're optically isolated. A 12-volt input will be detected, and we can use those for various things. One of the things we do different with this is we've introduced the Gigavac GX14 BAB series contactors. They have auxiliary contactors, and so when we close the contactor, we actually run 12 volts through the aux contact, and that goes to the LEDs. And that input also goes to our controller and lets us programmatically detect whether the contactor came on, which we don't care a whole lot about. What we really care about is, did the contactor go off? If for some reason you fire this battery into a huge capacitor without a pre-charge, say, it's possible to weld the contacts of the contactor. In other words, when they try to break, it draws an arc and welds them in position, and they can't open. That's a fairly dangerous situation for your battery, and so we note that. Your LED will remain on even though your device is off. Secondly, we get an input to the controller and can detect that we have a welded contactor. And so that's kind of important. So that's how we put it all together and how it works. I think we've got a good, safe system. I won't say any lithium battery is 100% safe, but we've done our best to use the BMS boards in the battery modules to monitor voltages and temperatures, and using contactors and high quality connections such as the Rebling, that will give you a pretty good chance of disconnecting your battery in the event of mishap or some miscalculation with your other equipment where it tries to overcharge the battery or over discharge it. And it will automatically prevent that, and you're able to configure what values you use for that. And I hope you do so intelligently. Okay, this is a quick look at our software for the module controller. Here we've got our 30 kilowatt pack with 6 modules, their voltages, their temperatures, and each cell voltage displayed right here. You see we've got 6 modules, 47.52 volts. Our average cell is at 3.96 volts. Our average temperature is 3.92 centigrade. Our health is 100%. Our stated charge is 66%. That's hadn't really been reset, so it's a little bit meaningless. But our Schneider MPPT charge controller, the 80-600, it's almost 7 o'clock here, and we're still doing 11.6 amps, 550 watts into the battery. And here's a count of our ampere hours and our watt hours for this session. Our configured battery capacity is 705 amp hours. Our demonstrated capacity, we have not discharged it past 340 amp hours yet, so that's all we know that it'll do for sure until we discharge it further. Battery lifetime charging kind of gets reset every time we recompile the software, but we're charging it, charged 0.58 kilowatt hours and discharged 0.03 kilowatt hours. And this will accumulate until you update your software, basically, and perhaps beyond that. We may be able to retain that through software updates. This gives you an instantaneous snapshot of your max system discharge current this session, since it's been up, And our max system charge current this session has been 51.61 amps. We're kind of scrolling up here because we're showing 6 modules. Let me see if I can disconnect here. No, that's not going to work because of the clear screen. Here we go. This is our software version and our runtime. And it shows you how many days, 0 days, 0 hours, 35 minutes, and 55 seconds. And I'll show you why that's kind of important in a minute. Our current high cell voltage is 4.01 volts. Our low cell voltage is 3.9244, and that's a real number, by the way. Our negative contactor on is our positive contactors on, and as I said, we actually get a 12 volt input from the aux contacts of the contactors. It's reported on, and the positive contactor is commanded on, and it is reported on. And if we turned one of those off and this was still reported on, it would actually give us a little advisory that we had a welded contactor. Our temperature alarm is off and we've had a 0 count. Our voltage alarm is off and we've had a 0 count. Our charge enable is on and our heat enable is off. Now, if you notice, a lot of this carries from one section to the next. You can power down your battery entirely and power it back up. Your state of charge will be the same place, not an amp hours discharge, and so forth. And your configuration items. Let's take a look at the configuration screen. Here we can set our battery ID at CAN speed for 2 CAN ports. Our inverter type, if we have one that requires CAN support, we've got 0 right now for none, but a 1 would be the Sunny Island. We can clear all the module faults, search for connected modules. We can reset the charge values to 100%. It's currently 66.26%, but we could, with a Z, we can reset it. When we're fully charged, we would do that. Clears alarm cycle contactors. L prints log to screen. I'll talk more about that in a minute. Here we enter our capacity manually, and this parallel is 3. We have 3 sets of 2 modules in series, and so we need to enter that so it knows our battery configuration. Our pre-charge is set for 10 seconds. Our high voltage alarm, where we would actually cut off the battery and disconnect it from the system for safety, is at 4.3 volts right now. Our low voltage is at 3. Our variance is 0.25. If we get more than that amount of difference between any 2 cells, we disconnect the pack completely. We have our high temperature alarm set for 45 degrees. Our low temperature alarm set for 5 degrees. Our cutoff and resume values, cutoff is at 4.15, resume at 3.60. That determines whether your charge enable is on and off, and that charge enable output is used to switch a Gigavac mini tactor, in our case, applying the solar PV voltage, the high voltage, 500 volts or so, to our MPPT charge control. Sensitivity 80, our alarm sensitivity, 1 is most sensitive, 254 is least sensitive. Well, we have encountered in testing simply anomalous alarms. There's nothing wrong with the battery pack, there's nothing wrong with the current, but we throw an alarm anyway, anomalously. And so this sensitivity setting is the number of times that can happen before you trip the alarm. Now, in the case of a real cell variance or a high temp or low temperature incursion, high voltage or low voltage incursion, that alarm would be thrown about 30 times a second maybe, or maybe more, 40 times a second. So on 80, it would still trip within 2 seconds. But we can handle up to 80 just anomalous events. And that keeps you from magically having your battery disconnected by an anomaly noise in the system that you don't need to deal with. Our log interval is 1. That means we're going to log data every minute, and we can log for 13 days. Now I can change that log interval to every 2 minutes. Let's say 2. And you can see that we can do data for 27 days. Would you believe the EEPROM we put in the EVTV DUI? EEPROMs are so cheap now, there's no point in putting a little one because they're not any cheaper than the big ones. We've got a 256 kilobyte, 256,000 bytes of storage in our EEPROM, and we typically use 80 of them to 100 to store these kind of configuration items, so you don't have to enter this stuff every time you fire up the system. That leaves a lot of memory, and I thought, well, it's not really a lot of memory by today's gigabyte standards, but when you're logging the current and the voltage and the power, that sort of thing, you can do a lot of that in a very little bit of EEPROM memory. And so as the calculation went on, we don't have an SD card or anything to do logs. I can probably add that, but you may not need it. We can simply log entries. Every 2 minutes gets you 27 days. Let's put a log interval equals 5. Well, that's 67 days that we can store, taking a data point every 5 minutes on your battery system and do it for over 2 months. And so let me go back to log interval equals 1. Well, if I can learn to type, we go back to 1. Let me hit a capital L here, and you can see this printing out the days and hours of our log entries. And we've got quite a few here. I'm going to hit an E. Well, this is just going on and on. I think we've overwritten some data. We've got voltages and so forth here. So I entered a capital E. We're going to erase our EEPROM log data. And so this won't be as dramatic. But this is actually what it's enumerating here is the pages. And each page holds 20 entries from our logging. And so what this is doing is erasing entirely each of the pages in our log. And we can do 1,024 pages, I believe, in our system. And so now we're logging, but it'll take 1 minute for us to do an entry now. So my EEPROM log data shows nothing with a capital L. And we're still charging at 11.79 amps. That's pretty good. Now, once we have this done, and we're pretty much there. What do we do with it? Whenever I put together something as a finished product, about half of our viewers like that, and the other half are like, Jack, that's too much money. I can build that same thing myself. Except I can't really build it myself without your stuff. And so I just want to buy the stuff I need from you, and I'll do the rest of it myself. If I sell it as piece parts, that satisfies that half, and the other half are like, well, can't you just put me together one? And so this is kind of complicated in the number of parts required and the programming required. And so I've decided to do it every which way. We will sell you this box with the batteries in it, and the modules would normally go for about $7,800 on eBay just for the modules. We'll sell you the whole box and the whole thing wired up and ready to go, as you see it here, for $10,000. So if you need instant gratification, want a 30 kilowatt pack, as long as there aren't too many of you, we can do that. But me and Dylan kind of have to put them together. The interesting thing about that, and I already have this up on the website, is every component in here, but maybe two, and I'll get them up, is already listed on our website under the Tesla battery module section. In other words, if you do buy this for $10,000 and you have some difficulty and need to replace any of the parts, I've got them all separately listed. The controllers separate, the LEDs are separate, the switches separate, the contactors, the rebling, every piece in the device is listed separately. That becomes particularly important when we come to wiring harnesses. You may not like this box. I even have the box in the web store. $499, we'll ship you the box. And I suppose we could do an assembled box without the battery modules. You get your own. The trick to all of this going forward, using the modules in the car or in a solar application, believe it or not, gets back to wiring. As we showed you in the assembly, our 70 millimeter connectors work great. We've made a special copper U-bar that lets you stack them, and those are available in the web store. This is a wiring harness for the shield, and the shield, the controller comes with a mating connector and pins, but this we had to make 24 inches of wire, and it's very high quality wire. It's already crimped and installed in the thing. So then you can take these ends, which are already stripped and tinned, and use those for what you want. Or if you're a little closer to a contactor or whatever, you can cut this wire shorter and connect it and minimize your wiring. So this will be in the web store. I think it's $29.95, something like that. And by the way, the company that makes our cables make a whole bunch of cables for Tesla, I found out. We have 3 ready-made harnesses for the battery modules. And this is the key to this thing. If you, this harness comes with the mating connector for this. We didn't install it because we have to run this through sometimes a gland nut or something to get outside of a little enclosure. And so you want to run the wires through and then add the connector. And that connector, which by the way is the same connectors used on the Tesla drive unit. We had them laying around, 12-pin connectors, they work good. And so this is a 2-module wiring harness that you plug into this, and you plug these into the BMS boards of the two modules, and you're good to go. And you can monitor those modules, strap them up as a 48 volt. That'll make you a little 10 kilowatt battery bank, and you're good to go. If you want a little bigger, we have a 4-port somewhere, a 4-port harness, and again it has this that connects to your controller, and then we have 4 connectors, then they're spaced just the right length, with the black braid and so forth to fit 2 side-by-side modules. And of course they go to the next level quite easily too, and so this would work perfectly with our 4 modules we have on the bench. But let's say you want to do more, and if you look at the diagrams on these, you'll see why this is kind of tricky. This is an expansion module, expansion harness. It does 4 modules, but it terminates in the same connector that the controller does. And so I can take this 4 and these 2 and plug this together, and I get 6 modules. I could also take my 4 and plug that into it, and now I get 8 modules. And in fact, between the 4 that are on here and terminating it with either a 4 or a 2, you can build harnesses to do any even number of modules up to the 62 that the controller will actually monitor, balance, and report on and control. Why would you want to do 62 modules? Well, also in the web store is a 36-inch wide, 72-inch tall, 30-inch deep version of this Wiegman enclosure. It weighs 488 pounds. I think I've got it in there for about $2,200. But you can put 54 of these battery modules in it for a 300 kilowatt hour battery pack. And these harnesses you can simply string together to wire all of them up. Why am I talking so much about wire harnesses? Well, I want to sell them. Actually, no. We spent a lot of time building the prototypes of these over and over and over again for different configurations of these batteries. And so I worked out this 4, 2, and 4 extender scheme so we can take wiring harnesses and string up as many as we want. Oh, say like 16 in the Cadillac Escalade. So not only can you put these modules in a box like this for your solar installation, but I think we could probably get 9 of them in here if we didn't have our electronics in this box, and squeeze that in under the hood for about 600 pounds, which is about what the motor weighed. And so we're going to replace the V8 engine of the Escalade with about the same weight in Tesla battery modules, and do the other 7 underneath, kind of in various places with our control electronics to manage the pack. So that's what we've been working on. I've also got some great work going on doing the same thing. We actually have a Tesla full pack leaned up against the wall and powering the shop, and with a 37 kilowatt charge controller that stops right at 394 volts. It's working perfectly to charge that battery, and resumes at 360 volts, I think, and that's working fantastic. So that's the plan on the solar, and most of those parts would work equally well on a vehicle to manage the battery. So that's what we're working toward, is where you can buy any of the individual parts. You can buy the box wired up, or we'll send you this one, and you can plug it right into your solar system. And at this point, the software is working. I imagine we'll be updating it weekly for the next year, but it's up and working, and I have a way for you to upgrade the software, which is not open source. I've got a lot invested in the software to run this little system. So that's kind of why the controller is going to be a little bit pricey, but I think it will do very well in managing, in combination with these wiring harnesses, with managing modules. What kind of enclosure you put it in and what kind of contactors you use, I don't care too much. But the concept is to be able to manage and operate these batteries usefully and safely going forward. And that's pretty much our show this week. Stay with us. Okay, we have taken a 85 kilowatt Tesla battery pack, and we have made no changes to it at all. In fact, I haven't even taken the plastic off the top of it. We did put some chains through some of the guardrail holes and took our forklift and brought it up close enough to the window to break the window, and set it down. It's leaning back against the wall. I've actually got a very sturdy iron bar here in this window set from the 1940s. The battery is completely, I don't think I could do anything to it from the pulling it over, but we zip tied it to that bar and positioned it kind of carefully between our stuff here. Here's our Wiegman battery connector and our solar controller, and we've got another solar controller over here. Actually, it does similar voltages, but it just doesn't quite handle the power like the other one. And so this thing is secured on the wall. Aesthetically, I like it to be flat to the wall, bolted to it, but I'm not too sure that's the thing to do. Right now, we're going to do this like this, and take our controller and plug that in down here, and then connect it in to our system, our 85 kilowatt pack. Here is a Tesla connector, probably not what we'll use. It's sort of a spring-loaded affair. We'll maybe some of this out of copper, and this is a Rebling T-handle. We'll run that into that right in here. And so we'll have an 85 kilowatt Tesla battery for our shop for the solar system. And it's kind of unmolested. We haven't even cleaned it up. It's just as we received it. And if anything goes wrong with it, I guess we can forklift that one out and slide another one in right in its place. Stay with us.